Good afternoon, everyone. So our next speaker is Rameez from AARNet. He's from Brisbane, and he is talking about detection as code and detection deployment at scale. So please welcome Rameez.
Hello everyone. Today I'll be talking about detection deployments at scale within the AARNet SOC. This is probably one of the most interesting projects I've worked on in the last few years, so I'm pretty excited to share our experiences. So my name is Rameez. I work as a security engineer at AARNet. I'm a bit of a jack of all trades. I've done a bit of DevOps, incident response, SOAR, malware analysis. I've generally just dabbled in a variety of different roles over the last couple of years. So a little bit about AARNet. We're a non-for-profit telecommunications company, and we specialize in providing services for the higher education sector. So I work within the AARNet SOC, and we operate as a managed security service provider specifically for the universities. So just a quick disclaimer, I'll be covering quite a bit. I'll only be taking questions at the end. You may feel like I'm speed running many topics, and that's because I am. It is a highly technical presentation, so the first 15 minutes are actually non-technical. I do recommend sitting closer just for the viewability of the slides. There's quite a bit of information available on them, and you might struggle to read what's on the slides. There are a lot of references to restaurants and Gordon Ramsay, so you sort of have to like Gordon. So today I'll be covering a broad set of, can you hear me still? Oh, can you still me? I think you lost me. We good? Yeah. So today I'll be covering quite a broad set of topics. We'll be looking at detection engineering, what a detection engineer does day to day, the limitations of manual detection deployments, the benefits of using detection as code, and then I'll be pivoting into the different tools that we use within our environment, and I'll be providing a brief explanation of each tool. So we'll be looking at our SIEM, Git, Kubernetes, Kubernetes operators, Helm charts, Helm, and Argo CD. After that, I'll show you how we stitch each of those tools together to provide or to build a comprehensive and scalable detection deployment. We'll also be looking at how we use Git to test, build, and release new detection packages. And right at the end, hopefully we have some time for me to cover our lessons learned, and I can answer any questions. So detection engineering. So detection engineering is a process of developing detections to identify threats within an environment, and it's a detection engineer's responsibility to carry out the detection engineering process. So the day-to-day of a detection engineer typically consists of reading threat intelligence reports or incident reports, doing some threat modeling, and trying to understand how an environment could be compromised, maybe some threat hunting, so proactively searching for signs of new or undetected threats, building detection rules to actually deploy to the various tools that they're using, tuning existing rules, so if you've got high false positive rates or a threat has changed the way it operates, you'd have to tune the rule. Usually you spend some time deploying the actual detection rules, which is what we'll be covering mostly today. And then they'll often be testing detection logic, so simulating attacks and then verifying that the detection rule operates as they expect. So when it comes to managing a very large MSSP environment, there are quite a few challenges if you take a manual approach for detection and detection deployments. So a manual detection deployment approach typically consists of an engineer going into like different web applications or tools, copying a detection or uploading the detection to the tool, and that's usually done for each customer. So detection engineers are quite expensive. The more customers that you have, the more time your detection engineer has to spend deploying detections, and therefore the less time is being spent on actually building detections for your environment. So for example, one manual rule change may only take 5 minutes, but you multiply this by 20 customers, and you're looking at around 100 minutes to make a change to a single detection rule across 20 customers. There's usually no approval process or a poorly implemented approval process, which is also hard to enforce. There's also no single source of truth. What you'll often see is a detection engineer might have like 10 different versions of a detection rule saved in different locations for different customers, which becomes quite problematic. The rules are also not tested automatically. They're usually manually tested, and because of the manual effort, detection engineers will frequently skip tests. They won't actually test the detection rules before they deploy them. There's also no single audit trail, and that's quite problematic as well. So what you'll find is you can't figure out why a detection engineer deployed a rule at a specific time or removed a rule from production. The whole process is quite prone to human error, and you'll often find dysfunctional or even just poorly tuned detection rules finding their way into production. So this is where detection as code comes in really handy. So the idea of detection as code is it's the practice of managing, developing, and deploying security detection rules using software engineering principles like version control, testing, and automation. So instead of having your detection engineer manually test and deploy rules, the rules are written as code, automatically tested and deployed through an automated standardized pipeline. So now we're going to take a quick look at our tooling, and I'll provide a brief explanation of each tool and how they work. So most of you have probably used Git. You probably know it through platforms like GitHub, GitLab, Bitbucket, all of which provides similar capabilities. If you haven't, think of Git as like a centralized library where you store your code, your scripts, your procedures, your recipes, all that sort of stuff. It keeps a full history of every change, who made it, when and why, so you can go back in time, review edits, or undo mistakes when needed. So Git supports approval workflows, which allows you to make sure that only the right people can approve important changes to certain files. And when you connect Git to automated tools, it becomes even more powerful. You can trigger deployments, security checks, and even tests whenever something is updated. So we also use Kubernetes heavily. It's typically used for deploying containerized applications. In our case, we use it to deploy Logscale, which is our SIEM, and our detection rules. So there are quite a few components when it comes to Kubernetes. The two most important ones in this case are, firstly, Kubernetes manifests. These are like instruction sheets. They're written in YAML. They tell Kubernetes exactly how things should run, what containers to use, how many, and what they need to function properly. Then you have Kubernetes itself, and that's like the system that takes your app instructions and brings them to life. It deploys your containers, keeps them running, and automatically handles scaling or recovery if something goes wrong. So I like to think of Kubernetes as like a restaurant manager, in this case Gordon, who manages and ensures that your kitchen is deployed in the way that you've described within your operating manual, which is your manifest, which you can see on the left. So let's say, for example, you want Gordon to be able to hire staff at your restaurant. Out of the box, Gordon can't hire staff. However, this is where Kubernetes operators come in handy. So Kubernetes operators, they're like software extensions to Kubernetes that help you manage things that Kubernetes can't handle out of the box or on its own. So in our case, in order to allow your Kubernetes cluster or Gordon to be able to manage chefs or hire chefs at your restaurant, you would need to install a custom operator for Kubernetes, which would then give Gordon the ability to hire and manage staff. So using Kubernetes operators, using Kubernetes operators does not change the way that you communicate with Kubernetes. And in our environment, like I said earlier, we use Logscale's Kubernetes operator, which allows us to deploy detection rules to our entire Logscale cluster. So you can see in the image here, we've got Gordon, which is just typical Kubernetes, and then you have me installing the whip operator, and now you can hire chefs. We also use Logscale as our SIEM, like I mentioned earlier. For those that don't know what a SIEM is, it's essentially like a big security information event management tool. It's like a big data lake where you store your logs. You would typically send logs like Windows event logs, firewall, Linux syslog into a SIEM. So tools like Splunk, Elasticsearch, Microsoft Sentinel, they all provide SIEM-like capabilities, which you might be familiar with. So now imagine you're opening multiple restaurants, and you want them all to follow the same recipe book, but with a few small differences, like the amount of each ingredient. So this is where Helm and Helm charts comes in handy. Helm is a package manager for Kubernetes, and it lets you define, install, and upgrade applications using Helm charts. A Helm chart is the package itself, and within a Helm chart, you can define templates for the generation of Kubernetes manifests. So the idea behind a Helm chart is that you can reuse the same recipe or template across different environments and feed in different variables or values without rewriting the recipe or manifest multiple times. So as you can see on the left of the screen, we have two different values files with different shop names and quantities of water. And then on the right-hand side, you can see we have our Helm template with the variables defined. Once you combine these within Helm, it will output two different Kubernetes manifest files, which we then apply to our cluster, or we give to Gordon to apply to the cluster. So Helm provides an extensive suite of functions for templating, similar to Ginger. If you've used Ginger before, you can have if statements, for loops, load files, folders, load files from folders. It allows you to standardize your deployments across environments with one templated config. It helps you reduce duplication as you only have a single template. You then use values files to swap in environment or customer-specific values or settings. Helps you accelerate onboarding. To onboard new customers or environments, you only need to define a new values file. It makes updates very easy as well. You make a change in one place and the updates roll out everywhere. It supports versioning, so you can pin customers to very specific versions or environments to very specific versions of your Helm chart, or even roll back to old versions of your Helm chart very easily. So on the screen here, you can see on the right, it's an example of what a Helm chart's folder structure looks like. So you've got the templates directory, which contains your templates like you saw on the previous slide. Then you've got the chart.yaml file, and this contains the name, description, and the version of your Helm chart. And there's a bunch of other directories and files that I won't cover. But one thing that's important to note here is that you can actually create your own folders, custom folders within a Helm chart, and load files, like I mentioned earlier. And we use this for storing our detection rules and loading them into our Helm template. So now that we've covered Git, Kubernetes, and pod deployment, there is one critical missing component. So how do we ensure that our files from Git make their way to Gordon so he can manage the restaurant? And this is where Gordon's Bugatti comes in handy, also known as Argo CD in this instance. So Argo will drive over to Git, fetch the Helm chart and the values files, and then load them into the boot. I actually don't know if Bugattis have boots, but and then from there, it will drive over to Gordon, who will make sure that he has the latest Helm chart and values. So in other words, Argo CD ensures that whatever is in Git is your desired state, is exactly what's running in your Kubernetes cluster. So if anything goes out of date or out of sync, it then notices and then redelivers. So Argo is also capable of managing and deploying multiple environments using a thing called application sets. The way it works is Argo will fetch each values file from your Git repository for each customer or environment. It then runs each values file through your Helm chart, which then outputs a Kubernetes manifest for each environment or customer. Then from there, Argo will hand these manifests to Kubernetes, which will then deploy each environment. So you can see an example I've got on the screen here. We have 3 different values files, one for McDonald's, one for Grilled, and one for Hell's Kitchen. Argo will then generate 3 different Kubernetes manifests by combining the Helm chart and the values files. And then Argo will drive them over to Gordon, who then creates 3 restaurants and makes sure that the appropriate services are available. So Argo has got quite a nice GUI. Unfortunately, I don't have time to show it. It's responsible, in our case, for monitoring Git repositories. It's also responsible for syncing whatever's in Git to our Kubernetes cluster. It actually periodically checks the Kubernetes cluster to make sure that the status and the health of resources is okay and reports back. It's capable of deploying multiple environments. It's used for enforcing state. An example being, let's say someone goes into our SIEM, changes a detection rule manually. Argo will then see that change and make sure that Kubernetes reapplies the manifest to overwrite that detection rule to what's in Git. It's also able to self-heal, so if it does sense something is wrong, it will redeploy a detection rule or repair a pod, you could say. And whatever is in Git, if it's removed from Git, let's say you delete a file or remove a detection rule, Argo will pick that up and actually delete the resource in your Kubernetes cluster. Will tell Kubernetes to delete the resource, sorry, which will then remove the detection rule from the environment. So at this point, everything I've covered is relatively simple. The next 15 minutes or 10 minutes might be a bit more complex. So what does our deployment look like at AARNet for detections? We have 3 Git repositories. Does that come out all right for everyone? Can everyone read that relatively easily? Yeah? Okay. So we have 3 Git repositories. We have a repository for our detections Helm chart, and this contains our detections and our templating logic. We have a repository containing our values files for each customer. We then have a repository containing our Argo CD configuration to configure Argo. We also have Argo, Kubernetes, and our SIEM, Logscale. So the way this works is Argo will fetch the configuration that we've defined within the Argo config repository. It then provides, Argo fetches the customer values files and the detections, I just went way too far. Argo fetches the configuration that we've defined within Argo's config repository. It then provides the manifest to Kubernetes, which then configures Argo, in a sense, with the application sets that we've defined. From there, Argo will then fetch the customer values files and the detections Helm chart from Git. It then combines them both and then provides the manifest to Kubernetes. Kubernetes then goes off and deploys and manages our detection rules within our SIEM. And then it periodically checks for updates to both the values, the customer values repository, and the detections Helm chart. And it does this for each customer that we have. So if we've got 20 customers, it deploys an application in Argo, or Kubernetes, you could say, for each customer. And it does continuously monitoring, continuously polls those Git repositories. So now I'll now move on to what each of our Git repositories contain, so you can have a better understanding of how they work. So here's what our customer values repository structure looks like. I'm going to cough. Sorry. That water got me. So on the left, you can see the structure of the repository. It contains a folder called customers. Within that folder, it's got the name of the specific customer. And then within that folder, you have any customer-specific configuration. In our case, it's the values file that we feed into our Helm chart. On the right, you can see what's in that values file. And this is a configuration which defines all the variables to be fed into our detections Helm chart. In the picture to the right at the very top, you can see the name of the customer. And then at the very bottom, you can see the folder in which we load our detection rules from. So just take note of that, those folders at the bottom, alerts defaults and alerts McDonald's, as I'll reference them on the next slide. So here within our detections Git repository, we have our Helm chart. And within our Helm chart, we have a custom folder called alerts. And then within that folder, we have a folder called defaults. Now, if you remember the file paths that I gave you before, or asked you to remember, they match the file path in the previous slide. So the way this works is that the values files defines the folders to load the detections from, and then we've got our Helm detections Git repository, which contains the actual files that values file is referencing. So how do we do this in Helm? We use Helm functions to load files from within the Helm chart. The templating code looks similar to what you can see on the screen, but that code probably won't work if you try to replicate it, as I've had to strip a bunch of content from it. So what does this mean for our detection engineers? Our detection engineers do not have to write Kubernetes manifests. Kubernetes manifests are quite large blobs of YAML. And instead, they write simple detection rules, as you can see in the top right. We then load that using a Helm and output the manifest automatically. So it keeps things very simple for our detection engineers. The Helm chart and the values files combination ensures that the detection engineer doesn't need to, it ensures that the right detections get applied to the right customers. So the engineer doesn't really have to think too much. They just drop the detection in the right folder, and they upload it to Git, and bam. So here we have our third Git repository, which contains our config for Argo CD. Within this repository, there's a YAML file with our Argo application set, which is what you can see on the screen. At the top, you can see where we define a generator. And this essentially tells the Argo application set to generate an application based on the files or folders stored within Git. From there, we then defined what the application should look like below. And at the very bottom, you can see where we define the file path, so the URL for our Helm chart detections package. So once again, this is roughly how it looks end to end. The detection deployment pattern has proven to be incredibly efficient, scalable, and easy to maintain. We've been operating with this model for about 2 years now. I could probably calculate the amount of money this has saved us. I'd say it's in the millions, as we've been able to ensure that our detection engineers push out a lot more detections and don't have to worry about deployment. So in the last 2 years, we've had about 1,222 total merges. We've triggered around 1,085 package releases, which I'll cover later. And this triggers a deployment to production. We have about 280 rules per customer. So you times that by 20, so that's a lot of rules. That's automatically being maintained. It's really low maintenance, and it's self-pruning and self-healing. So we don't, once we make that commit and that merge to the main branch, it just does magic and it deploys. So here we have a rough high-level diagram of our testing and release process. Sorry, I should have said, we'll now be moving into CICD. So here's a rough high-level diagram of our testing and release process. There's 3 components that I'll be covering. So first one being Git merges and approvals, our detection tests as seen in the blue, and then how we package, version, and release detection updates as shown in the orange. So here's how we manage merge requests for detections. So detection engineers will log into GitLab. We use GitLab. They'll review all the merge requests that are currently pending or are waiting for approval, and which you can see at the very top. When the detection engineer navigates into one of the detections, into one of the merge requests, they'll be able to review the tests executed and the approvals pending before the detection can be merged. So currently, we have a relatively simple approach when it comes to detection approvals. We only require one detection engineer outside of the committer to approve the detection rule before it can be merged. However, we do require all of our tests to pass. We also do have this one edge case, which I'll briefly explain. Our analysts, we have documentation stored within the detections Helm chart for how our analysts handle alerts that are raised from these detections. Whenever an engineer updates that documentation, we actually require an analyst to approve the change an engineer has made to the detection triage guidelines. We do this using, I think it's called code owners in GitLab. So there's 5 different tests that we use for our detection rules to validate them. Actually, more specifically, our detections Helm chart. So we've got Helm lint, and this checks if it validates that the values file has the correct structure so that Helm can generate templates. Then we have Helm template, and this executes the templating code. We run this to validate our templates can actually be generated. So it's more so testing the template itself. We then have a Helm unit test. And this checks that our Helm templates output the correct keys and values when we provide it with various inputs. We then use YAML lint. This ensures that our detection YAML files stored within the chart have a valid structure. And then we have an alert validator script. And this actually tests the actual detection rule itself and ensures that the detection rule itself is syntactically correct. So at the very bottom, you can see an example of where all of these tests have passed within a merge request that was raised by an engineer. But due to time constraints, I'll only be covering the very 2 bottom tests, as they're probably the most interesting ones. So for our detection rules to be deployable, the detection rule needs to contain a very specific set of fields. An example of a detection rule can be seen on the left. So it's quite easy for a detection engineer to accidentally forget to add a field to their detection rule, like description or alert type. And if they do forget to add a field, it will cause Helm to return an error when the detection rule is deployed by Argo. Sorry, that's wrong. It will cause Helm to return an error by itself. So to make our detection engineers' life easier, we have written a JSON schema which then explicitly defines the criteria of what fields must exist for the detection rule to be valid. This can be seen in the picture to the right. We then feed our JSON schema and our detection rules into a tool called YAML lint as a CI pipeline, and this then validates that our detection rule contains required mandatory fields and values. We also have code editors to validate the YAML. We've configured our code editors to validate the YAML, and this allows our detection engineer to see live as they build the rule within the code editor what fields are required, what's missing, so they can easily fix the changes on the fly instead of waiting for the test to fail in Git. I do highly recommend everyone look into using JSON schema if you need to validate YAML or JSON files particularly if you have custom internal tools that require a very specific structure, or a custom structure, you could say. So when we first started using our deployment pipeline, we quickly noticed that our detection rules would fail to deploy due to invalid queries. The team would then reject these rules, and Argo would continuously attempt to redeploy the rules, and this caused a self-healing loop. We also have several internal standards and requirements to ensure that our detection rules work correctly when a detection fires, as we need to do reporting and metrics. So we need to have certain very specific fields in our detection rules. So to address this, we built a Python tool, and that validates our detection rules. It checks for required fields, syntax errors, and other issues. So we run this tool as a CI pipeline across all of our detection rules. So in this slide, you can see an example test configuration where we require the user.name field in our rule. And then below that, you can see a sample report from our script highlighting the rules with warnings or errors. So we'll frequently use this report. It's automatically generated as part of a CI pipeline. And our detection engineers will review that report and also if you're reviewing someone else's detection rule, you'll review the report to make sure that they haven't made any mistakes. So how do we release detection updates? So whenever we have to push a new version of our detections to production, we create an archive version of the Helm chart, and we give it a version number. This is also known as a release branching strategy in GitOps. One of the reasons we use the release branching strategy is because we want to be able to pin customers to very specific versions of our detection rule packages. So to determine the next version, we use semantic versioning, which is a versioning standard for software development. So semantic versioning is quite simple. If we push a non-breaking fix, we increment the patch release. If we push a new feature or detection rule, we increment the minor. If we push a major breaking change, we increment the major. So in this case, because Gordon's pushing a breaking change, we would increment the major. So to version and release packages automatically and save our engineers time, we use a tool called semantic release. We run semantic release as a CI pipeline on our detections Helm repository. And when it executes, it reads the commit messages, determines the next version number, decides whether a new package release is required, it generates a change log, and it publishes a new Helm package to Git with the appropriate version number. So how does semantic release determine how many versions to increment your Helm detections package, or whether to increment it by a minor or major? It essentially just reads your commit messages, and based on the message format, it will then assign the appropriate outcome based on the config file that you've defined for semantic release. So on the right, you can see an example config. I've just simplified that with a table on the left. So we've got the commit message. Let's say it's fix::ABCD. When you push this into main, it will trigger semantic release to run, which will then determine you need to create a new package at a patch release. So it will it'll increment it by a patch release, and then it will create a new package. If you push a test, though, it will increment it by a patch, but it won't release a new package. It's really handy. You can do all sorts of stuff with semantic release. If you're doing, I highly recommend using it. You can do so much. I converted Colby into a loyal semantic release user. So here's an example of what a Helm package chart looks like after semantic release has packaged up the Helm chart, generated a changelog, and pushed a new release. So you can see you've got Gordon playing the role of semantic release. You've got your Helm chart in the middle. At the top right, you can see the detection package that was generated, which is just an archive. And at the very bottom right, you can see the changelog, which was automatically generated based off the commits using semantic release. One other thing that's worth mentioning is you can actually fully customize how it generates changelogs. So you can change the logos or the icons it uses or the structure of the changelog that it automatically generates. So here's the CICD processes once again. For those of you who want to take another look at it, I also have a full, more complete diagram at the very end, as this is simplified. So just a quick overview. We use a single source of truth with this model. All detections are written as code. We do versioning automatically, testing automatically. Our release processes are fully automatic. Our deployment is fully automatic. Creating a package is automatic. Detections are self-healed, pruned automatically. It's very easy to audit. And we can actually enforce approval processes by Git. So lessons learned, there's quite a few here. The solution scales actually really well. We've actually assisted other SOCs in deploying an exact copy of our setup. We gave them a bunch of stuff for files and able to spin up exactly a replica of our environment using the setup. I do recommend using environment branching instead of release branching if you're working on the same thing. Specifically, detection Helm charts. Debugging detection deployment issues can be quite hard. There's quite a few steps to the way the process works, so you need to spend quite a bit of time finding where errors are. I do recommend writing lots of tests, so don't spend too much time debugging deployment issues. It does require a relatively skilled engineering team to maintain. Yeah, writing Helm templates is a very painful thing to do. Yes, I haven't heard of anyone that actually enjoys writing Helm templates, and it is highly dependent upon a well-maintained and functional Kubernetes operator. So if you're using Splunk or something, and they don't have a Kubernetes operator which allows you to deploy detection rules, well, then this won't work. But if you're, let's say, like in our instance, we found that when we began deploying detection rules initially to Logscale, we found numerous bugs with the operator where rules weren't being deployed or removed properly, so we had to reach out and make bug reports to have those, the operator fixed routinely. If the operator is not supported very well, then you may hit issues with copying this deployment pattern.
Thanks, Rameez. You're doing amazing work, man. Like it's saving millions of dollars. Here's a little gift from AUSCERT. There's a few questions actually, a bit out of time, but I guess what the one from one of very attentive person in the front row. Why Gordon Ramsay?
When I started making the presentation, the best way for me to explain Kubernetes to someone who doesn't understand Kubernetes was via restaurants. That's what I felt. And then at some point, I realized that Gordon Ramsay fits in very well, so I had to redo all my slides and add Gordon.
It's awesome. Well, I'm sure if you want to catch up with Rameez later on, he's around, he's in Brisbane, and we'll sure he'd love to share information. So thank him again.